Welcome to the video number 5 in the Foundations of Computational Economics course. Today we continue talking about Python essentials, and we'll talk about control flow and user-defined functions. The plan is, just as I said, the background information is still can be found in the Kevin Shepard's book on Python for econometrics. So what's flow control? That's basically the rules, the operators which we use to design in which order different statements in the program are executed. First of all, there is branching, which depends on some conditions. That's the operator if, with its modifications such as else, if else, or if elif, and else. The main thing I would say to remember here is that in Python, not like in many other languages, the loops, the blocks of the code, are defined with indentation. So whatever block is the control should branch into is defined with some white space, and there's no closing operator. That is very nice, actually. That makes the code neat by definition, and it removes some clutter. So let's look at the examples. In this block of code, x is going to be an integer 2, y is a float, z is a list, and we can check some conditions. Right? If then we have a logical expression, actually all the way to the semicolon. And if this logical expression evaluates to true, then control passes inside of this block of code and observe this white space before print. Else, if this first expression is false, then the next one is checked, which is marked by elif, else if. If the first one is not met, the first condition, then the second condition is checked, and if that is also not met, then the catch-all remaining sort of condition is executed, else. Okay, so what do you think is going to be printed here? 10 seconds as always. Oops. There we go. Okay, so let's see. If y equals 2, and this is shaky, right, because we are comparing a float to an integer, but maybe z of minus 1 greater or equals 0. That's possible. If y is less than 2, condition 2, and condition 3 is... So let's see, condition 1. Why is this possible? So why did this comparison go through as an exact truth? Well, that's because the float 2.0 in binary is represented pretty much the same way as the integer 2, or it can be converted without loss of information, should I say? Right, 2 is representable in binary. Okay. What can we change here so that things get a little bit more interesting? What about y greater than 2? Which condition will fire now? Well, now the first one is not going to be satisfied. The second one is not going to be satisfied, so it must be condition 3, which is the catch-all else statement. All right, what about here? X is true, y is false. If x and y, else if x and not y, not x and y, not x and not y. Which one is it going to be? And let's fire the jingle again. All right, so x is true, and y is false. So we need x and not y. So condition 2 should fire. Right. Now, do you think that condition 5 could ever be executed or printed here? This is an interesting case where 4 conditions for these 2 variables, they essentially cover the whole space of possibilities. And I would say this is this is how the better code looks like. So using of else is absolutely efficient and possible in many situations. But in this one, it's redundant. And a lot of the times, covering explicitly the space of all possibilities is something that may prevent bugs on such long if statements. Okay, an interesting statement is a pass statement. It does nothing, but it's needed in Python so that a correctly defined block of code can be written. So pass is there only to preserve the indent, essentially. So this would work, but if we just delete pass, it throws an error because else is appearing unexpectedly, right? What's after if and then logical expression, semicolon, the interpreter is expecting some white space and then an operator, which in this case it's pass. Do nothing. Now, there is also what's called a ternary conditional operator, and that's basically an if in one line. Let's see at this in this example, a, b, and something called condition are initialized to 1, 3, and true, and then we can write things like a if condition else b, and the result of this expression is 1, which is a, because condition is true. Now, if condition is false, then the result of this expression is b. This is an expression, not a statement, and therefore we can assign it to a variable c, for example, and then we can print out c. This is very useful to be able to write code more compactly. All right, let's look at loops now. Looping is an essential part of any programming language, and machinery and the toolbox is pretty much the same everywhere. It's for loops, while loops, and then breaks and continue. In Python, there is an interesting case of being able to put else at the end of the loop to check under which condition the loop was stopped or the loop ended. Again, remember about 4 spaces to denote the blocks of code that are within the loops. And let's look at some examples. Here's the syntax for organizing a loop, for loop in Python. It's done with a variable which takes values from a given list. Okay, in which case, in this case, I is going to be taken sequentially values of 0, 1 up to 5, and we just print these values. This print basically leaves an empty string. And here the same example, which is achieved with the use of the operator range. Range essentially does the same thing. It allows I to take values from zeros all the way to 5, but as we can see, not including 5, which is a very important distinction. In Python, all the indexing is always done starting from 0 and up to, but not including the upper bound. A range works with the same philosophy. Now, instead of doing an explicit loop, there's something which is called least comprehensions, which is also a very nice Pythonian way of writing more complicated code compactly. So let's see what's happening here. X is initialized to be an empty list first, square brackets, that's list. And then for 15 steps, right, I ranging from 0 to 14, including. If I is divisible by 3, Remember, this $sign is the remainder of the division. So if I is divisible by 3, that's when remainder is 0. We append a list and we add item I. We add a string element to the list which says item I, and then we just print the list. Okay, what do we get? Item 0, 0 is divisible by 3. Item 3, 6, 9, and 12. List comprehension allows to achieve the same thing in just one simple line. Well, maybe less simple, but one compact line. The syntax is like this: square brackets to define the list, and then we have to say what are the elements of the list, give it a formula, followed by the operator for in range, and then we also can add a condition. So this one line represents exactly the same as 4 lines of code in the example above. And as you can see, X in the end becomes the same list as before. Now, the list comprehensions can be more complicated. So in this example, we are using I, j, which is going through the zip of two lists. One is the just indexes from 0 to 3, and another one is A, B, C, and D. Right? Look, there are 4 elements in each of these two lists, and then zip is an operator which combines this list element by element, and it's supposed to both have the same number of elements. And then doing it in this way assigns I and j elements of each of the lists. You can see that I takes the values, and we're just printing the I and j values. I takes the values from 0 to 3, and the same time as j takes string values from A to D. Similar effect can be achieved with list comprehension, although here we're doing something slightly different. Observe that there are 2 4s in this list comprehension expression, and that more or less covers the possibilities, the previous example and this example. X is going to be taking values from the tuple 2, 3, and 5, while Y is going to take values from the range up to 5. Because of this 2 separate for operators, unlike zip over here, this is going to combine all values from the first list with all values of the second list. And in the end, what we get is the formula is x to the power of y. So we have the elements of x taken to the power of y, which is 0th power first. Am I doing it wrong? So it's the elements of the list x taken to all of the powers up to 4, right? And then again, the second element of the list taken all the powers up to 4, and then finally a third element of the list x taken to all the powers. Okay, the bottom line is that we get all combinations from 2 separate for operators in the list comprehension. A very interesting use of the operator else for loops allows us to check how loop was finished. So in this example, we initialize k with 0, and then I is going to be going through the range of values from 0 to 99. Now, if I is divisible by k, then we will increment k by 1. Okay? And as soon as k gets up to 15, then the operator break will take us out of this list completely. That's what break is for. Else statement is executed when the code goes all the way up to the last value in the in the list of possible values without breaking out of the loop. Let's make it this capital letter, and let's see. Loop completes with k equals 16 and I equals 76. Okay? Now, what if we incremented k not when I was divisible by 5, but when I was divisible by, I don't know, 25? Then, as you can see, the loop completed with k equals 4 and I equals 99, but that means that I went all the way up to the upper bound in this range, and therefore else was executed, and we see this the line that was printed in this case. Be careful again with all this indents. You can see that this is a separate block of code, and inside of each if there is a separate block of code for break and k plus equal 1, and the same thing here. So all this white space in this little example has its meaning, matters. So let's look at slightly larger example of organizing a flow control in the code. We will write a short code to implement the sieves over Rathfens, which is a famous algorithm or ancient algorithm of finding prime numbers. So what's the algorithms? The algorithm's fairly simple. We have an initial list of numbers which will contain primes in the end. And then we just go through another list, a list of divisors, and cross out all of the integers divisible by each of the divisor. Of course, divisors themselves should come from the list of prime numbers and not just all integers. And we just continue doing this all the way up to a boundary that is predefined. Now, as I go through the listing of the code on the next slide, you all should think about how this algorithm as implemented can be improved. Improved in the sense that how can we make it run faster? So here's the code. First of all, let's define an upper bound on the set of these primes that we want to generate. This is going to be, we're generating the primes up to this upper bound, 23 to start with. First, we want a list of integers starting from 1 and going all the way to the upper bound. And by adding this 1 over here, when we call range, we are allowing the upper bound to be included. Now, we want to make sure that the object in the primes is a list, actually, because the range is a slightly different object. Initial divisor is going to be 1. And here's the main loop. While true means that all of this code here will be executed infinitely unless we break out of this loop. And as you can see, there will be breaks and continues in this loop. What happens here? Well, first, let's look at the next divisor. So we increment divisor by 1. Because we start with initial divisor 1, that means that the first actual divisor that we will be working with is 2. Now, if divisor is greater than the upper bound on the list of primes that we want to generate, that means that we've gone through all of the divisors and we can safely break out of the main while loop. This is this break. And what's going to happen next? Next control will go past the block that belongs to the while loop to line 17, where the result is printed. But if divisor, if we didn't break out in line 7, so if divisor is below the upper level, then we check whether divisor is itself in the list of primes. Remember, primes is initialized with all the integers between 1 and the upper bound, unless something is deleted from it. And as I said just before, we don't really want to spend time on crossing out the numbers which are divisible by not a prime. So if the divisor that we're looking at happens not to be in the list of primes that we already identified, then we can continue. What happens then? that means that we continue with the iteration of the main loop without executing the rest of the code inside of that loop. So we are not executing this commands, and instead on this continue, if this condition is satisfied, this continue takes the control all the way back to 4 and 5 to look at the next divisor, just to check whether the next divisor would be on the list of already identified primes. Okay, by line 10, we have the current list of primes or candidates from primes, and the divisor which is on this list. And so now we just go through the list of primes. So while I is less than the length of this list primes, the length will change, right? Because we are crossing numbers out. Initially, it's quite long. It's all the way to it's essentially equals to the upper bound. But what do we do on each iteration of the main loop? We see if the primes of I, so the element of this loop, is not equal to the divisor itself, but is divisible with this divisor. Again, this the percentage sign operator is the remainder of the division. And so this means that the number, the prime that we're looking at right now, the ith prime, is divisible. But we have to leave the first one in the list of primes, right? So it shouldn't be equal. So if these two conditions are satisfied, then we remove the element of the list which equals to that particular prime, to the one that we just identified, the one that satisfies the conditions. And so we remove the element of the list becomes shorter, and now I indicates the next element in this list. So I remains the same, the value of index I remains the same, but now because the one element, the ith element was removed, now in its place there is next element, right? And so we continue this loop of checks with the same I. Otherwise, if we didn't remove the element from this list, then we have to increment I to look at the next element of the list of potential primes when we're checking them against this particular divisor. Okay, so this section of the code removes all of the numbers on the primes list which are divisible with a particular divisor. And then just to make sort of a debugging output, let's print this divisor. And let's print the primes which remain after we crossed out everything divisible by that divisor. All right, let's run this code. Look at this. We didn't print initial list. We print the list after all the numbers divisible by 2 had been crossed out. And here they are. All of them divisible by 2 except the first one, right? So 2 is here, but none of other even numbers are in the list already. So 4, 6 is already crossed. Then on the next iteration of the big loop, the next divisor is 3. 3 is not greater than the upper bound, and 3 is still on the list. Here's the list of primes at the second iteration. 3 is still in this list, and therefore this condition is not satisfied, not on the list. And therefore we go into this loop and check and eventually print this divisor 3, and the remaining primes which are there on the list after we crossed out everything which is divisible by 3 except 3 itself. And then the algorithm continues, but see, there is no divisor 4, and that's because once we went to the next iteration and divisor here becomes 4, it's still less than the upper bound, so we don't break. But it is not on the list of the current primes. The current list after divisor 3 is this one. 4 is not there, and we don't need to cross out anything divisible by 4 because there are none in that list already. And so we can just safely continue to the next divisor, which is 5, and then we continue crossing out the numbers. Right? When the divisor becomes larger than the upper bound we set up front, then the algorithm stops and just prints the primes up to 23. And I hope this is right. Yeah, I'm quite certain this is right. Now let's comment out the debugging output and put some large number in here. Now, do you think these are all the primes up to 2023? Well, 24 would be the same. That's pretty neat. So the algorithm works, and here you can see how we can use the flow control where we make the algorithm loop into bigger loops and subloops and check different conditions, and you know, make it quite fast to calculate the primes in this way. Now, as I said, it would be nice if you think about how it can be improved even further. All right, the second part of this lecture is to do with user-defined functions. So user-defined functions are essentially blocks of the codes which we can call independently. A user-defined function has arguments which are inputs, so it takes in some data, works on this data, and outputs some results. The usefulness of these functions stems from the fact that we don't want to write usual typical operations many times in the code. In order to avoid that, in order to avoid repetition of the code, we write user-defined functions or functions and call the functions instead of rewriting all of the commands itself. Dogstrings, as you will see on the next slide, is something which is very important. Docstring is the first few lines in the user-defined function which explain what it does. And I cannot overstress the importance of these little helpful lines, because functions are pretty useless if we don't understand what they are doing. And believe me, even you, after some time, may forget what that function that you were writing was supposed to do. So here's an example of a function. The keyword here is def, so definition of a function, then the name of the function, and a semicolon. So this is similar to the flow control syntax with ifs and loop operators. As you could imagine, the block of code that belongs to the function is defined by the indent, as done in Python, and the function has to have a return statement if it returns any arguments. So this function does not take any arguments, input arguments, which would be in between these brackets, and returns 0 every time it's called. Now we can call functions from the main body of the program, which are not indented. So this is the main body of the program. X is my function, print x. So this is the way we call functions, right? The important part is the brackets in the end of the function's name. That's how we know that we are calling the function, and Python knows that we are calling the function. And the return is stored in this variable x. We can print what the function returned. The docstrings are immediately helpful if we just say help and then give the name of the function to this routine. We'll see that a nicely printed help statement tells us here what this function is doing. The input arguments of a function are given in the following way. They are listed in the brackets in the function definition here in line 1. And you can see this function here can take inputs A, B, and C, where C is already given a value right there. Well, that's a default value, so C can actually be skipped. And then if that's the case, at the call of the function, then it will take this particular value here. As you can see, the function returns a list composed of the 3 inputs. Now, let's try to see how we call this function from the main program. So x is going to be a return value. I can call the function with just a list of some values. 0 and string test. This way of calling a function is referred to as using positional arguments to assign the values. 0 will be assigned to A, which is first in the function definition, and test is going to be assigned to B. And as you can see here, the print out of the return of the function has 0 on the first place and test on the second place, and then we didn't even give C on the function call, and therefore C has the default value of 5. Now in the second call of this function, we are actually using what's called the named arguments to call this function, and we explicitly saying that A should be equalized to 1, a string 1, C should be equal to 3, and B should be equal to another string spelling 2. You can see that here A, B, and C are not even in the right order, but because they are named, then the assignment happens in the appropriate way. And so the result from calling this function is going to put string 1 on the first place and as A, 2 on the second place as B, and C in this case is given, so it's going to be it's going to equal to the value 3. Let's talk a little bit about the variable scope. The functions are very useful not only because they allow to put a piece of code together to be reused by the main program, they also separate the space of the variables from the variables used in the main program. Now, in this code example, you can see that there is a nested function, myNested function, inside of the user-defined my function. And this is also well possible. And moreover, we are having this hierarchy of the spaces where the variables exist. So look at this. The myNested function takes arguments C and D and does something with them. It returns their sum. But I have 3 lines of code here which are printing all of the variables in the scope of that function of where these lines are executed. So we can actually see what variables are defined inside of the nested function here. And the same we can do for the function my function itself. We can also list all of the variables which are defined within this function. And then outside in the main program, we have variables x and y. And here we're just calling my function with this x and y. What happens to them is that my function returns a times b times my nested function of a and b. And this a and b become the inputs in my nested function, which returns the sum of the arguments. But let's run it and see what different variables, which variables exist inside of each functions. So first of all, my function variables, so the execution goes like this, right? It starts at x equals 10, y equals 2, then the call to my function, this thing is executed, and then control goes in here, and then lines 9, 10, and 11 are executed. And therefore we see here first the outputs from those lines. So what are the variables defined inside of my function? Well, they are a and b, not x and not y, as you can see here. So x and y do not belong to the namespace of my function. They don't exist inside there. Only the arguments or some other variables that could be defined inside of my function exist there. And such a variable which is defined inside of my function is actually my nested function. My nested function is something that only exists inside of my function. And here it is. Here it is. It's a variable which holds the function itself. Okay, then as we call this expression here, a times b times my nested function of a and b, then we go inside of the nested function, and there we can see that only variables c and d are defined. And anyway, c, we called it with 10 and 2, so the return is going to be 10 by 2 by 12. And I believe that's right. And that's what happens here. So as we write the code, we should be aware of where the variable, each particular variable, where is it defined, where it is defined, and we can use to our advantage the fact that the functions have their own space for the variables to make the code cleaner and more readable. Now, a nice way to define short functions is called the lambda function. Look at this code here. We could say the f of x is simply x cubed, right? And the way to write it would be to say, def f of x and then return x to the power 3. Well, this can be written in one line. As you've probably noticed, tendency, Python has ways of writing longer constructions in a short way. So a lambda function is very useful because it allows to define the x cube as a function of x using this syntax here, and just save this function in the variable y. And so you can see here that we can say, f of 5, or we can then just call y of 3 as if y was a function itself. And in fact, it is a function, just defined with this one-liner lambda. Let's look at this one final example of the user-defined function and go back to the memory usage case that we looked at in the previous video. To be able to make plots, first let's define a helper function, myplot. It has one input argument, and the input argument is essentially data. The data will come in a form of a dictionary with fields x and y. And you can see here that we're using the matplotlib library. We'll come back to that when we talk about data visualization. And we're plotting this a line using x and y data in the axis, and we're basically putting some labels on the axis. Y axis is going to show the size of the memory used, and the x label will show steps of variable update. Let's see how it goes. So I first run this, then nothing happens because Python just basically remembers there's this function. And the main work is going to be happening in the memory usage, which is also a user-defined function with 3 arguments, as you can see, a variable, the grow, and steps, which is defaulted to 10. What does it do? So here's the docstring. The function returns data on memory usage when a variable var is grown using supplied function for given number of steps. So here var is the variable and grow should be a function. So this function takes another function as an input argument. What happens then is that a dictionary is defined, and then similar to the previous video, there is a loop that goes for a given number of steps, and variable is grown, quote unquote. So the variable is somehow increased. Remember, we were adding one symbol to a string or taking the square of an integer, things like that. And then the lists in the dictionary are grown as well. Oh, they initialize to the empty lists, I should say. All of these fields of the dictionary are initialized to the empty fields. And then we append, so add to the list v, we append the current value of the variable, and then x holds the number of steps. That's I. Oh, we want it to start from 1 rather than 0 to make graph more visually appealing. And then the size of the memory that's taken by the variable var. Okay, so that's the function. Let's try to use it. So first, let's try to use it on a string. The variable is going to be just a string with a star, 1 character. See, here's the usage of lambda functions. We need to pass a function to this memory usage routine. And an easy way to do it is to just define the function in place, right? Lambda is going to be a function on x, which will return an x plus another star. So it will grow the string by adding another star. And we want 10 steps of that. Oh, I have a bug here. Which is interesting. Sys is not defined, so we forgot to import the library that holds the size, the get size of the memory footprint function there. So let's correct that. And here's our graph. So it took 10 steps from 0 to 10 of the updating of the variable var. And if you remember, it started somewhere around 50 bytes. And as the string grows, more and more characters are added to the string, then the size in the memory grows linearly. What happens if we add 3 characters at a time? And to do that, I'm just changing the lambda function here. Well, hopefully you can see that the slope of this line increases. So we're adding more length of the string at each step, and therefore it takes progressively more memory space. Okay, let's call this function with there's an example where we're calling the x times 2 with the same string variable, right? So multiplication is actually defined for strings in Python, and what it amounts to, it's basically taking the same string twice. That's what we're doing here. So the first string is 1 star, and then 2 stars, and then 4 stars, and so forth. And as you can see, we get exponential growth of the memory that is needed for holding this growing strings. Now let's look at this example. We got an integer first, it's 1, and then we take the same lambda function, so we multiply an integer by 2 every time, and we're doing 200 steps now. So let's see how that looks. Oh, this is quite interesting. As you can see, an integer takes the same amount of memory as long as that memory is enough to hold the integers of those sizes. And then suddenly, when it gets out of that space, more memory is allocated by by Python automatically to accommodate the bigger value of the integer. And that happens many times over the course of 200 steps. So you can see how Python automatically adjusts the amount of memory allocated for storing these variables. What about this example? This is a large integer that grows in the same way. Let's try to run this. And what do we have here? Oh no, sorry, this is not an integer. This is a float. And in fact, this float, even though the incremental function is exactly the same, does not change the memory footprint, as we learned in the last video. So floats are bound to the same amount of space in the memory, but they can run out of that space, and that creates the special value of the float. Okay, we didn't print the last value. Okay, that's fine. This was the nice example on the memory usage. There are some further learning resources today as well. I would particularly attract your attention to this formatting of the output tutorial that is useful to learn how to print out various variables in the programs. Till next time.